at the Catholic University of Leuven from 2000 to 2020, and program director of the Bachelor Master of Science of Biomedical Engineering from 2016 to 2020. As of October 2020, she is a professor emerita with duties. She received a master's degree in computer science engineering, computer science and engineering, a postgraduate in biomedical engineering, and a PhD in electrical engineering from the KU Leuven in 81, 85, and 87 respectively. And during that time, she actually worked on that book that we all know of. It is the on total least squares. It's definitely a book in the area, well known in our field. She was a guest professor at Stanford University in 2000 and Uppsala University in 2002. She is a member of, a fellow of IEEE, SIAM, and EMBS, and a member of the Royal Flemish Academy of Belgium. Okay, and in 2013, she received an honorary doctorate from Eindhoven University of Technology, along with an appointment as a distinguished professor from 2014 to 2020. She has built up a large group of biomedical data processing research group, over 30 people. And she has a renowned expertise in numerical linear algebra, multilinear algebra, biosignal processing, machine learning, and AI, as well as the development of numerical algorithm software and their application in biomedical and multimodal and multi-channel processing for improved medical diagnostics. She has supervised over 80 students, and in 2014, she received a 5-year grant from ARC on biotensors. One question is, how do you do all this? It's amazing. You have been extremely productive. I'm always inspired when I look at your productivity in the past. I'm really humbled to see all the work you've done. Really amazing. So let's welcome Sabine.
Thank you very much, Youssef, for the introduction. Thank you, Tulin, for having invited me to present here challenges in smart patient monitoring. And especially, I would like, in fact, to show you how you can use the different techniques that you learn here during this summer school, how you can apply this, in fact, in medical applications. Oh, what's that?
Oh, maybe this one. Just rough it was working.
Otherwise,
Yeah.
otherwise I stay.
I think the better maybe. Oh, this is. Okay, press harder.
You think so?
Yeah, I really press hard.
Okay, so I will introduce the topic, present the research overview of medical fields I would like to handle here, and then we move to the key technologies. So I will talk about blind source separation, tensor decompositions, and AI, moving from machine learning to deep learning. And then I will show you how you can apply it in several examples, and then come to a summary of future challenges when you want to bring these techniques, in fact, into medical practice. So we will start from a multitude of data that you can acquire using wireless devices, using imaging devices such as NMR scanners, wireless body area networks. So Also, you can use your iPhone. So we acquire a lot of data, but you would like to use this data in patient monitoring for monitoring chronic diseases, acute diseases such as cancer, stress, sleep monitoring, etc. But what you need is our powerful algorithms to transfer or to extract, in fact, interpretable diagnostic information from this data. And that will make your patient monitoring smart. And so I will talk about how to make, in fact, your algorithms smart. This is important because the hospital of the future will really move to the home environment. And this is possible because we have a lot of unobtrusive devices. We can do multimodal measurements. We can do long-term monitoring, but we have extra challenges to face. More artifacts because we only deal with wearable devices, so of low quality. We have to deal with big data. And of course, therefore, we need to automate the algorithms. So in close collaboration with the hospital, I work in 6 different fields, and 4 of these I will treat during my talk. So wearable health monitoring, very important. Using wearable devices, we move really medical diagnostics to a home environment. And this is possible to monitor cardiac patients, to monitor patients during sleep, and to monitor patients who have rheumatic diseases. Second field, neonatal brain monitoring. We monitor the brain of neonates in order to protect the brain as much as possible, which is really important for their life quality. So how can we do that? I will tell you how to protect the brain when these neonates have epileptic disease. A third field I will not treat here because of lack of time is our signal processing algorithms you can use to analyze neural activity when you use high density probes, which are in fact invasive devices. Fourth field is data integration. Just take 2 heterogeneous sources. We want to integrate that in order to generate new information. And I will tell you how to integrate EEG, electroencephalography, with images, functional magnetic resonance imaging, in order to localize in a better way the onset of epileptic zone. Fourth, we have mobile EEG becoming increasingly important. And one of the big, nice application is to use neural devices. I would say neural, you extract neural information in order to improve hearing aids. So these devices or the neural information can be used to know which speaker the user wants to attend. And in this way, you can improve the hearing quality. And the 6th field is cancer diagnostics. And in cancer diagnostic, you integrate information from anatomic MR images with spectral information in order to better localize, let's say, the most aggressive part in a tumor. The techniques I want to use here are tensor matrix factorizations that you also learn in the course. And I will complement this with techniques from AI, where we move from machine learning to deep learning. So let me concentrate first on these technologies. And the first one I want to treat here is blind source separation. So we start, in fact, from raw data, let's say 3 channels that you acquire on the scalp. And we assume that these, the data here can be written as linear instantaneous mixtures of underlying sources, but we don't know the sources and we don't know the mixtures. So how can we quantify the information? Well, just use factorizations. So we start from the measurements, we put them column-wise into a matrix, and then we factorize the matrix. But of course, we need to add extra constraints in order to come up with one solution. So matrix techniques combined with constraints such as orthogonality and dependency leads to 2 solutions. However, these constraints are rather artificial. So we can do better by using tensors. Just move or just extend each channel in the frequency dimension in the end, you can get a tensor matrix. And then you can decompose this tensor as a sum of rank 1 tensors. This is the most popular tensor decomposition that you can take, the so-called canonical polyadic decomposition. And what I need to do, in fact, and the challenge is not only to develop or to compute this mathematical decomposition, but to interpret all these components. So these components must have a meaning in the medical context. So how can we do that? So we can also use extra constraints in order to better or to compute a decomposition which makes the factorization more interpretable. So let's continue with these tensors. And of course, I don't develop my tensors myself. I work with my colleague, Leuven, who has developed a very powerful tensor MATLAB toolbox. You can also use tensor toolbox, of course, from Tamara Kolda and her group. So in TensorLab, you can decompose the tensor as a sum of rank 1 tensors, but you can do more. You can also decompose the tensor as a sum of low rank tensors. And if you just restrict it to just one term, you have the Tucker decompositions, or if you assume an all orthogonal core tensor, then you have multilinear SVD. So all this is available within TensorLab, and even more. You can do so-called, you can use structured data fusion, and in that way factorize simultaneously multiple tensors, where in fact some of the components are linked to each other, or are common over different factorizations. Here you can impose structures such as tuplet structure, Hankel structure, or orthogonality, or non-negativity. And the goal, or in fact, the way in which these factorizations or joint factorizations are solved is by formulating the problem as a nonlinear optimization problem in a number of parameters that we need to quantify. In AI, well, AI is not new. In 1950, AI started, but the first focus was on the implementation of knowledge systems. However, in 1980, computers could learn, in fact, from images. And in first instance, they extracted information in terms of features and then tried to classify the data. But more powerful algorithms were generated from 2010 on, where deep learning allowed, in fact, computers to learn directly from the raw data, from the raw images. So let me explain the concepts of machine learning. And we take here as example that we would like to discriminate two types of animals, the llamas from the alpacas. So what we do is we ask, let's say, a farmer to just make a number of pictures and label the pictures with the correct class label, like you see here. And then if you want to generate an algorithm which discriminates both classes, you will first look for discriminating features, such as the angle of between the ears, the angle of the ears, the relative shoulder height, or the relative length of the tail here. So you do this for all these animals, and then you pick or you select those features which are most discriminating. And you can then, in a two-dimensional graph, put all these images that you have acquired. And then try, in fact, to separate both classes. We call the data training data because we know the label, and we will design a decision boundary, in fact, which separates both. But there are multiple solutions, like you can see here. Some are better than the other. But the best solution that you can find to separate both classes are those that maximize the margin between both classes. And this is, in fact, a concept which is used in a very popular family of machine learning algorithms the ones which are based on support vector machines. So we have a decision, an algorithm that makes that decision, and then you can just use new data that you haven't seen before, and these data are called the test data. And then using the boundary, you just classify the new data into the correct class. So this is called supervised learning, because you start really, you make an algorithm based on data with correct class label. But you can also work with, you can also do unsupervised learning, where you don't know, in fact, the class label. So again, starting from that graph, then you look, in fact, whether you see independent clusters, when you see independent data sets, and try, in fact, to characterize these clusters. And indeed, that's what you see here. You see, in fact, two clusters. And the better, in fact, these clusters match, in fact, with the real classes, let's say the llamas and the alpacas, the better, in fact, the more powerful this unsupervised clustering is. Now, if you have new data, you need, in fact, to assign the data to the correct cluster by computing the distance to the cluster centroid, and the smallest distance gives you, in fact, the class to which you have to assign the new test data. So in machine learning, whether you work in a supervised or unsupervised way, you start from feature engineering and feature selection, and then from these features, you want to develop a classifier to classify the data. But in deep learning, you start directly from the raw data, and the feature engineering is, in fact, integrated into the with the classification into the same algorithm. So let's move to deep learning, and I only discuss one class, the most popular class, which is the class of convolutional neural networks. Here we start, in fact, from patches, I would say, where you take a convolution with a certain kernel, or you call it a filter, and you reduce that information to a more condensed part here. And then you move, in fact, that patch over the whole image in certain steps. We call it strides. And in this way, you can cover a feature map. And you can, in fact, generate several feature maps, which is, in fact, the depth of a certain layer. So this is one layer convolution, but then this will be followed by a compression. And for compression, you can, for example, take the maximum in a certain area, or you can pool the data by taking the average. And you move the data in a sequence of different layers, of course, with the goal to automatically extract meaningful features. And at the end, you just take the compressed features that you just concatenate, let's say, in one long file. These data are then used for classification. And here you will have a number of dense layers in order to come to the right classification. Okay, I will use these technologies now to show, in fact, how you can use this in cancer diagnostics, neonatal brain monitoring, for data fusion and wearable health monitoring. So let's first look at cancer diagnostics, where I will show you the power of tensor factorizations. So here I start, in fact, from an anatomic image where you can see the presence of a tumor area. But you don't know where the tumor is, where the core of the tumor is, where you have necrotic tissue. Therefore, you need to add spectroscopy. So spectroscopy will put a grid here and in each voxel over this grid, you acquire one spectrum. And we call this magnetic resonance spectroscopic imaging. So a spectrum looks like the picture you see here. You see a number of peaks, and each peak corresponds to a certain metabolite, which resides, in fact, in that voxel. So you have choline, creatine, and acetyl aspartate. You have lipids present. What's important is, in fact, that this spectrum characterizes an underlying tissue. And the goal now is, in fact, to characterize that tissue. So we take all the spectra here and we just put them column-wise in a matrix. And then, okay, we can use factorization. So we apply one of the techniques that you learn here in the summer school to generate a matrix W and H. And W should contain sources. And these sources should be interpretable. So here in my context of brain tumor tissue typing, I look for sources that represent normal tissue, tumor tissue, and necrotic tissue. And you see that the underlying spectra are quite different. And the H matrix tells you how much each of these tissues is present in one particular voxel. And in this way, you can generate color images with voxels that have dominating normal tissue here, voxels in the tumor area and voxels in the necrotic tissue. This is a generic technique that you can also use to characterize prostate cancer. You can add extra artifacts as additional sources. So here I added non-negativity as an extra constraint since all the data I started from are non-negative. So it's NMF, which is a very popular technique that you can use. But you can do better. You can also move to tensors. So if you take these spectra and you generate a two-dimensional image of that, and order all the voxels one after the other in the third dimension, you start from a tensor. And this tensor can also be decomposed using non-negative canonical polyadic decomposition. Using tensors, you can even do a better characterization of the tumor area. When you only use NMF, the technique will fail to characterize some of the tissues in some cases. Like you see here, the tumor is not well represented. It should have this banana shape, but it fills, in fact, the whole area. The same when you use any extensions of NMF, such as hierarchical NMF. But using tensors allows you to better characterize the tumor, necrotic tissue, and the healthy tissue. And you can even add more classes, which represent here, in this case, additional artifacts. The second application of tensors in spectroscopy is that we want to get rid of components or irrelevant components. So if you take spectra that represent metabolites with the proton in the chemical structure, then you will need to have as annoying factor the presence of water. Water has 2 protons in its chemical structure, and we have a lot of water in our body. So if we take we take spectra of metabolites having a proton in their structure, we need to deal, we have in fact a very large water contribution, which is 10 to the 4th, maybe larger than the metabolites we would like to quantify here. So to have reliable quantification, we need to get rid of this water contribution. And how do we do that? What we need to do is, in fact, to make this region where you have water, to suppress it completely. So what we do, in fact, is that we model the spectrum as a sum of damped exponentials. We can do it in the time domain, or equivalently, you can do it in the frequency domain. And we need to quantify, in fact, the parameters within the model. Again, you can do that. I don't show how to do that, but the kernel technique to use is, again, a factorization. Now you can do the factorization voxel by voxel. And this is done if you use a matrix-based water suppression. But you can do better. If you order the data in a tensor where you take all the spectra together, then you can in fact do better because you use the information of all the voxels together, and you can model this the water component, in fact, over all these voxels. So if you do that, you can, using a tensor-based technique, better suppress the water in the water region and indeed obtain a better quantification of the underlying metabolites, such as in prostate cancer that you see here. We have a high presence, or we have the presence of huge components in choline, which characterize the tumor area, and which are in fact better characterized if we use a tensor-based technique. The most recent application where we use tensors in spectroscopy is in fact in deep learning. So in deep learning algorithms, you can use an extra layer where you use tensor factorizations or matrix factorization. And here I illustrate this. I add an extra layer in a deep learning algorithm, which is called a factorizer block, and where in fact as kernel step, you use a negative matrix factorization. Using matrix factorization or tensor factorization allows you to reduce the number of parameters. So that's one important advantage. You compress the parameters and you have less parameters to quantify. But more importantly is that if you add such a step, you also have components in your deep learning algorithm that are better interpretable. So here we applied on brain tumor segmentation. You see here a tumor with necrotic area, the tumor area, edema. And if we then show some of the components that result from the deep learning algorithm in the shallowest layers, we already recognize, in fact, the tumor here, but we have better separation of the different tumor areas if we move to the deepest layer components. So using such a factorization block allows us to do a brain tumor segmentation which better matches with the ground truth. Okay, let's move now to neonatal brain monitoring. So why is brain monitoring needed here? Well, the most modern or modern neonatal intensive care units have in fact separate boxes where the children are lying, I would say. So what happens is, in fact, that these children can reside in a more I would say in a more quiet environment, but on the other hand, the nurses don't have a direct eye contact with these neonates. So they need automated algorithms in order to control the status of these babies. So monitoring or automated monitoring is important here. And here I will focus on the brain, neonatal brain monitoring. So most of the children that are admitted to the neonatal intensive care unit are prematurely born infants or infants that suffer from a hypoxic insult. So this means that it's during birth, suddenly due to complications, there is they got shortage of oxygen supply, which means in fact that there is a risk or indeed there can be brain damage. And then you need in fact to see how the brain is recovering and decide whether you need to treat the baby, and in this case they will cool the baby in order to protect as much as possible the brain. Of course, because neurologists cannot work, I would say, day and night, we need these automated algorithms. And here I focus on electroencephalography in order to develop adequate tools. So we start from several sensors, which are put, in fact, or pasted or glued on the scalp of the baby in order to start the monitoring process. So if there is any brain damage, then often you will see neonatal seizures that emerge. So these seizures are abnormal, excessive and synchronous neuronal activity in the brain that you will see in several of these channels, I would say, that have been acquired with electroencephalography. And you can recognize these seizures by an increase in amplitude, which then decreases again towards the end of the seizure. Also, there is a dominance in the lower frequency range. And you will see also some spikes which are repeated over time. One of the challenges is, in fact, that neurologists have also difficulties in order to recognize these seizures. So raters can disagree in recognizing these seizures. So we have to deal also with incorrect labeling when designing these algorithms. So now I will show how we can detect seizures using, in fact, 3 families of algorithms. And the first family that we developed are, in fact, we call it a heuristic approach, where we try to mimic the neurologist. So if a neurologist wants to detect seizures, he or she will look at the EEG and look for specific patterns. And typically you will have an oscillating pattern, or else you will have a spike pattern, or in half of the cases you will just have a mixture of both, like illustrated here. In the orange part we have oscillations, and in the red part we have the spiky pattern. So what you can do is that you develop in parallel 2 algorithms, one to detect the spiky pattern and another to detect the oscillatory pattern. In the algorithm, it's built in 2 parts. First part, you look for the changes relative to the background. And in the second part, you look, in fact, for the repetition. So you need also a repetition. And if you have detected a seizure in one of the pipelines, well, then you say, yes, I have detected a seizure. So this is an algorithm which have been implemented in a graphical user interface in the hospital. So on these channels here, you see the ongoing EEG. And once the algorithm detects a seizure in one of the channels, then the information will be displayed here, the duration of the seizure, the type, whether it's spike train or oscillations, and also in which channel you see the seizures. And then also what you can do is that you can display on a topographic plot one of the features which characterizes the seizure, and display with the red color whether there is a seizure present or not. So you need to improve these algorithms. And one of the improvements is to do a pre-processing of the data by removing artifacts which lead to false detections of seizures. So these artifacts, common artifacts, are cardiac artifacts coming from the heart, from respiration, from blood vessel pulsation. And for each of these artifacts, you have to take, in fact, a dedicated blind source separation algorithm. So you see here some spikes coming from an ECG artifact in some of the channels. And using a blind source separation algorithm, you can indeed get rid of these spiky artifacts, and in this way reduce the number of false seizure detections. So this is one family. Another family is we use machine learning, and a popular algorithm here was developed by Temco from the group in Ireland. Typically then you start from labeled data set with labeled seizures, and you extract important features. So features in the time domain, in the frequency domain, or from information theory. And these features are then fed to a classifier. So here we use a support vector machine classifier. There is some post-processing in order to develop an algorithm. But we can do better, and indeed more recent algorithms will use deep learning. And the first algorithm that was developed was by O'Shea. And so here feature engineering is integrated with the classification. And we have also further worked on this algorithm and improve it by taking more steps, so more layers, in fact, in the deep learning architecture. As you can see here, we work with different channels, and so we apply, in fact, the convolution on segments within each channel. So you use a number of layers here that you condense, in fact, to compress features, which are then given to the classifier part. That here you can also change this classifier part in the deep learning architecture with, let's say, a random forest model. And if we do that, we could improve, in fact, the detection of the seizures. So let us compare now these three families in an ROC curve. This curve displays, in fact, the sensitivity, the number of correctly detected seizures with respect to the number of alarms. So for the heuristic algorithm, we have an accuracy of, let's say, around 85% correctly detected seizures against 50% alarms, false alarms. And this accuracy is also reached by the deep learning algorithm. The algorithms based on machine learning have a lower performance. But an additional advantage of using deep learning algorithms is that at runtime, in fact, the computational speed is much faster because we don't need to learn or to quantify features. So we have a computational speed, which here in this case here is about is a factor 100 times faster. So that's an additional advantage. Okay, let's move to EEG fMRI data fusion. So we combine here, we take EEG by putting sensors here on the scalp of a patient. That, of course, so these we use typically around 20 sensors, so we will have only a limited spatial resolution. On the other hand, we have here an excellent temporal resolution using these EEG time series. And we combine it now with fMRI images where indeed we have a very good spatial resolution here to quantify the areas or to visualize the areas which are active. On the other hand, the temporal resolution of fMRI is really not good. But we hope by combining both techniques that we can integrate, in fact, the strength or combine the strength of both. And so we apply this in an application. So also to detect epileptic, to detect, in fact, the zone where the epileptic seizures are originating. So why is this important? It is important for patients that cannot be helped by medication, but patients that have, let's say, a focal seizure. And we hope that by reducing tissue, so the brain tissue where the seizure is originating, that these patients can be seizure-free after surgery. So in the pre-surgery phase, we would like to localize that zone as good as possible. So one of the techniques is then to put the patient with an EEG cap in the scanner. And we look, in fact, into the EEG for spikes. So these are spikes pointing spikes. We call it epileptic spikes. So it's not during a seizure, but between seizures, there is epileptic activity present which is visible in the form of spikes in these EEG channels. And these spikes will generate or will activate some of the brain regions. And these activations of the brain regions due to these spikes can be made visible in the NMR, in the functional MRI images at several slices. So, but there is one challenge here is in fact that there is a difference in scale. So the spikes here are fast electrophysiological changes. So but these spikes, it's like an impulse, and the impulse response comes only later in terms, let's say 1 minute or so. It's really a slow reaction. We have to transform, in fact, these spikes using a hemodynamic response that we have to also estimate in order to transform the information from the spikes to the time series that characterize the information in the fMRI. So to quantify that information, we can use joint tensor decompositions. We ordered the EEG can be ordered in a tensor once we extend, in fact, each channel also in the frequency domain. So we start from time frequency profiles that we order here into a tensor, and that we decompose in the best way as a sum of rank 1 tensors. And the images, the fMRI images, are put into a matrix where, in fact, we split the different areas here into brain regions, and then look, in fact, how they these evolve over time. So we have a time moment here, and we have different regions in the horizontal direction. So that we also need, of course, a hemodynamic response here. So it's a complicated relationship, that we can condense all that information into one joint tensor matrix factorization, where the information, in fact, that you see here, the time pattern that you see here, which shows the spike pattern here, is matched to the time information here into these MRI images. So what we need to do is to look for the time series into our EEG and see, in fact, how this corresponds to the time to a corresponding time pattern into the fMRI. Once we have found this, we can then look, in fact, we can then look into or we can translate that information into the fMRI images to look, in fact, which areas are active or activated due to this spike pattern, or this pattern of interact or epileptic spikes. And also information can be extracted from the hemodynamic response, but I will not further treat that information. So how do these patterns look like? Yeah, this is the PhD student who was working on that. It takes really 4 years before you can develop, I would say, and analyze the data and come up with this structure. So that he managed to do that and come up with this structure. It's a very nice piece of research, but I would say to use it in a clinical environment, it's still too complicated. So if you look at the components, the 3 components in the canonical polyadic decomposition that we have. You take the component, the temporal component, which best matches with the spikes, and then you know, in fact, that the corresponding spatial pattern gives you information about also the localization of the epileptic seizure activity, and the spectral pattern gives you information mainly in the low frequency range. Okay, let's move now to wearable health monitoring, where indeed in wearable health monitoring, we will preferentially deal with sensors that offer comfort to the patient, so which are non-obtrusive, and so an important physiological signal is the cardiac signal. So if you go to the hospital for an ECG, then a standard ECG will involve, in fact, 10 different electrodes that are pasted at standard position on the body, and they will generate 12 different channels. So a channel is, in fact, a lead between two different electrodes, and what you want to visualize is, in fact, a projection of the electrical activity on these different leads. So in practice, it looks, the signal that you acquire is characterized by a number of characteristic peaks, PQ or ST, but the most important one is, in fact, the R peak. And the R peak coincides with the contraction of the ventricles so this is a very powerful muscle contraction, and this is needed to eject the blood into the aorta. So this R peak is visible very clearly into the ECG. And it's important information because it allows you to quantify one heartbeat, and you can quantify the length of a heartbeat, or 1 over that length gives you the instantaneous heart rate. So in practice, we will not deal with all these sensors, but we will just take 2 channels, 2 electrodes, and on one lead, we will acquire such a signal. Which is, of course, and you can do this by just some patches or 2 electrodes that you paste on the patient's body. Of course, using these wearables are data of low quality. So we need to develop quality indicators to find segments of sufficient quality, so clean segments. So therefore, we develop algorithms to quantify the quality level. And the quality level depends on the diagnostics you would like to extract. So if you would like to extract information which is only related to the big R peak, then you can just take low quality data because, as you see here only there is a large part where the R peaks are missing. So we need to eliminate that segment. But if we need a better quality of the data, then we will need to eliminate more segments and increase our quality level. How do you find these quality indicators? Well, here we just used machine learning. So we started from a variety of recordings, one from sleep, one from stress, another one from a public data set, and we invited some raters to label the data as clean or noisy. And of course, these raters disagree about some of the segments. These are the segments, of course, which are questionable whether they are noisy or clean. But in any case, that labeled information allowed us, in fact, to develop a continuous ECG quality index based on machine learning. And indeed, it's an algorithm which gives us a fast result and an accuracy of 99% for the detection of the noisy segments. So this algorithm is used, certain and very useful, using wearable data in order to eliminate the clean, not the clean, but the noisy segments. So also important when you would like to do seizure detection in a home environment, not a clinical environment, then you will preferably probably not use EEG, but you want to use just an ECG patch and look, in fact, for changes during the seizures. So if you look for changes during the seizures of let's say, a signal which displays the length of one heartbeat, so the RR interval, you will see that the RR interval becomes shorter during a seizure, which means that the heart rate increases during a seizure, and also the respiration rate will also change. So we need to capture these changes in order to detect seizures. But we will do more. So we have the challenge to automate seizure detection in a real time in a home environment. So to have more reliable seizure detection, we will not only use ECG, but we will combine it with other wearable devices, such as a wristband, which measures movement, so-called accelerometry. We can use an EMG device to measure muscle activity, and we can also combine it with EEG. Of course, the EEG, nobody wants to wear a cap, and that's why we are working on new devices. And one of the new devices where we integrate, in fact, all these measurements is this CZIT prototype. It's one device that you can wear just behind the ear, and it integrates the EEG measurements, of course, only one channel, EMG, accelerometry, and ECG. This is developed in collaboration with the big pharma company UCB, which makes a lot of drugs for epileptic seizures. So we extract information here, features which are then fed to a classifier to develop a reliable seizure detector. And you can further improve that seizure detector with supervision, with supervised personalization. So we can ask the patient to give feedback when a seizure occurs and use that part of information to make, in fact, the classification algorithm more person specific. So this is needed, in fact, to monitor patients offline and send the information to a neurologist. And in this way, the neurologist can see whether a patient who is changing medication or needs to change medication, whether the change is medication is successful or not. Another application, very powerful, which is close, I would say, to clinical practice, is in fact sleep monitoring. So the classical, if you have sleep problems, then the classical examination now is within a hospital, where the patient, in fact, has to stay during one night in a hospital bed with a lot of sensors, wide sensors. So this is not very comfortable. So we would like to change that to a monitoring environment within the bedroom of the patient using less obtrusive wearable devices or even contactless devices, such as a wristband that we can use, or we can use just an oximeter, something that you attach only on the finger, or more importantly, you can just integrate sensors in a contactless way in the mattress. And here we use ballistocardiography, where we measure, in fact, the body's recoil caused by cardiovascular pulsation. So in an indirect way, these measurements or these devices gives us information about heart rate. And from that information, we can also derive information about respiratory activity. So we use, in fact, these devices, of course, having a lower quality of information, but we can use them over a longer time and also multiple nights. And you can use this to control your sleep pattern. So see whether the patient is awake in sleep, whether you have deep sleep or not, so different sleep stages, and also to discover, in fact, sleep problem. And one of the most common diseases is sleep apnea, obstructive sleep apnea. So these are obstructive sleep apnea are in fact events during the night or multiple events during the night where in fact you have an occlusion, a partial occlusion or a complete occlusion of the upper pathways, of the upper airways, in fact. So this means, in fact, that your breathing is stopped, and then you have to act, or your autonomous nervous system will become activated in order to restart the breathing. And this will evoke, in fact, a kind of micro awakening of the patient. And it will, so what will happen is, in fact, that the sleep pattern of the patient is fragmented, so the patient will not have a lot of deep sleep and will become very tired during the day. So we have to treat that if the number of apneas that the patient gets will become too high. So in summary, we want to get rid of the clinical examination. The clinical diagnosis is highly accurate, but it's really cumbersome and uncomfortable. So let's move to a comfortable, unobtrusive sensor environment where we can do measurements during multiple nights, where we capture the normal sleeping pattern, but also we can do large-scale monitoring. So here you see these apneic events. So in the breathing pattern that you see here, which is nasal pressure, you see really stops in the breathing pattern, apneic events. And these apneic events will generate, in fact, I would say, reductions in the oxygen saturation that you can also measure with an oximeter at the fingertip. And as I told you also, the breathing need to restart, and this will be usually, therefore the patient will probably have so-called an arousal, and this typically will increase the heart rate. So due to an increase in the heart rate, breathing will restart again. So you see all these changes in the signals that we can need to capture in order to detect in a reliable way sleep apnea. So to control the severity of sleep apnea, we compute the so-called hypopneic index, which is the number of stops in the breathing or breathing reductions during 1 hour. So if that number of apneic events is above 15, then we say the patient has sleep apnea and we need to treat the patient. So severe apnea starts when the number of apneic events during 1 hour is 30 or more. So we would like to detect apneic events and also to detect, in fact, the severity of these apneic events using wearable devices or unobtrusive devices. And one of the first challenges I take here is, I take a commercially available sensor, the so-called MFIT sensor, which is a pressure sensor. So if we take that sensor, can we then automate, can we use that, in fact, in order to detect apneic events? So what we do here is using this ballistocardiographic sensor, we can monitor the respiratory activity, but as you see, there are a number of artifacts, and artifacts usually we need to get rid of the artifacts, but here they have a lot of, they carry information that we need to extract here. So we look, in fact, for features which characterizes these distortions in the respiratory signal that we capture with this contactless device. And so the features that we compute here quantify, in fact, the variance of the peak-to-peak amplitudes. And they characterize, in fact, the clean segments. They characterize information here, which can be detected and revealed here using unsupervised clustering. So using unsupervised clustering, we can derive here a cluster of clean segments versus a cluster of artifact. And what you can see here is that the more apneic events the patient has, the more artifacts we will have. This is also made clear here. We have the different classes of apneic events, from no apneic events to more severe events. And if we display here a measure of data irregularity, we see indeed that there is an increase with respect to the class of the severe apneic events. And this is quantified by the distance, in fact, to the centroid of the clean center. So data irregularity can be used as a marker of apneic events and can be used as a potentially useful technique to screen patients in a home environment. Secondly, we can detect patients using, or we can use, in fact, just a subset of sensors. Take the sensor which measures breathing information and the sensor which measures ECG information. So these are wearable sensors that we use in the clinical environment, but we can also use these in a home environment. And now we make use of the power of deep learning algorithms to deduce features using deep learning on the ECG segments and using deep learning on segments that we derive from this respiratory activity as extracted from the thoracic belt. And then combine these features into a multimodal deep learning network in order to quantify the probability of sleep. Is the patient awake or is the patient asleep, in sleep? In sleep, we developed this algorithm based on patients that don't have any apneic events. And then use this algorithm, in fact, on a data set of patients that have apneic events. So if we do that, we need, in fact, to derive two additional thresholds, a threshold above which we are confident that the patient is awake, and a threshold below which we know the patient is asleep. But there is a whole zone here where the number of, we don't know, we are not certain whether the patient is asleep or not. And this is information we can use in order to detect, in fact, the severity again of this sleep disease. So the hypothesis is that we have more uncertainty in the prediction of sleep and wake in patients having these apneic events, and they have also more awakenings, which means there are more transitions between sleep and wake in these patients. And so we will use that information. We use that information, the number of sleep-wake transitions and the number of uncertain sleep epochs, in order to select, in fact, or to design, I would say, an algorithm, an easy algorithm to detect, in fact, patients that have severe apneic apnea. So this algorithm gives us about 80% accuracy for detection of severe apnea. This is a simple algorithm which can be further refined using other information. But the important is that you can use wearable sensors to develop already and have a simple algorithm for detection of this, or to do a first selection in a home environment of patients that have a risk for apneic events. And you can even go one step further by using the same algorithm, in fact, on sensors that you integrate into a mattress. So no longer use sensors on the body of the patient, but do the same measurements of heart activity and respiratory activity in a bed environment, into the mattress environment. So do it in a contactless way. Here in this, we use here bioimpedance. Here in this environment, there is no extra improvement by combining the ECG measurements with the respiratory measurements. Contactless respiration is here powerful enough in order to derive, in fact, an algorithm that have similar accuracy as the one using the wearable sensors. Well, somewhat less, but it's in fact a very promising environment. And if we further increase, in fact, these algorithms, we could come to a more reliable device, I would say, to do detection of the severity of these apneic events into a home environment. Okay, so let me come to the future challenges. We have a number of, we have lots of applications where tensor decompositions, matrix decompositions, deep learning can be used in research applications, but how to bring this to clinical practice? There are still a number of hurdles to take. First of all, the hardware needs to be further improved. We need equipment which is even more wearable, more contactless, more reliable. The software needs to be more reliable because we need to use the software during multiple nights. We need to deal with big data with low quality. Furthermore, we need validation centers, not only in one center, one hospital, but in multiple centers. And here the challenge is, in fact, that the patient data need to be labeled. Also here, there is a lot of uncertainty. It's labor intensive. We have severe data regulations, data protection regulations. And finally, also the nurses need to be trained to learn about these algorithms. And finally, we need, of course, to bring the technology to the market. Also here, the stakeholders, they need to face ethical issues, business issues. You need to apply for CE and FDA approval, which is also very challenging. And moreover, we deal with small patient populations. We have a large societal value, but the economical value is really much less. Why? And that's why commercial companies don't hesitate, in fact, to put a lot of effort in developing technology for, let's say, for neonatal monitoring. Okay, I would like to thank you for your attention. I would like to thank my research group for helping me in developing, of course, all these technologies. Thank you very much.
Any questions?
I have a question. You mentioned the low rank models, and I wanted, so in the, thank you. So I would, okay, so you mentioned about low rank models. We know that in tensors, rank is not something which is uniquely defined. So I was wondering, how do you use it in your tensor factorizations? Is it something you prescribe, or you use it based on some error? Prescribed?
That's a very important question. Yes, all the rank, the algorithms to find the rank in an automated way, they cannot be used in these applications, or they lead to a rank which is way too high. So we need to use prior knowledge coming from the application itself in order to find a reasonable rank, in fact. Or we have to find it using cross-validation or so other techniques. And usually the rank is really, should be small. So really, the most successful applications are those where the rank is restricted to 3, 4, 5, so not a rank of 20.
You had a neural network that had a layer that had non-negative matrix factorization. I wonder where the matrix come from. Is that the feature is a matrix, or is it the matrix of features in the minibatch?
Yeah, you have to take one of the layers. So in the deep learning network consists of a number of layers. So we just take the information from one of the layers and then apply it and apply then NMF on the information in that layer. So it's really, it's like you have different layers. So you just add one layer and you take the data from the previous layer that you have to order, of course, in a matrix or in a tensor. So you have to tune, in fact, what's the best structure to do that.
So it was several layers.
Yeah.
Okay. Thank you.
Yes, yes.
Yeah, very nice talk. So I think in the medical and healthcare domains, there are a lot of times will be time series, and they are actually very easy to go into high order tensors. So you presented work about using more numerical methods to do the factorization and understand the factors. And then later on, there are also machine learning and deep learning methods that try to do the factorization, and from there we also have the factors and try to interpret them. So I'm just wondering, I mean, so could you comment on these two streams of methods? Do you feel that, I mean, so maybe one stream will be actually more promising than the other ones, or maybe they are complementary, or just it is really, I mean, this may not be actually this question may be actually a bit having different answers, but it's really more about comparing traditional numerical methods versus these deep learning methods. So what do you find about the strengths and weaknesses from either side?
Yeah, okay, what's the question now? It's do you mean deep learning using tensors compared to deep learning without tensors?
Or maybe we are not doing deep learning, it's just traditional factorizations like SLS factorization or
In deep, you mean in the machine learning or the deep learning?
Yes, so I guess, I mean, so we can also do deep learning in order to get those factors, right? So we don't need to exactly do the factor or do the CP. So it's just different methods. It doesn't matter. It's just in general. So there may be some ingredients about running neural networks and getting something out of it. So are you actually seeing benefit from there, or?
Yeah. No. Okay. You can do deep learning and then extract the information without the factorizations. Here we are just exploring, in fact, what are the benefits of using factorizations as an extra layer. So one of the, in fact, the advantages are to decrease the number of parameters. So in this way, we can have computational speed during the learning process. And on the other hand, in fact, we can make some of the components more interpretable. But it depends on the applications you're working on. So the application of brain tumor segmentation really is successful, but we also try to apply the same technique in multiple sclerosis, where we are looking for lesions. The lesions are really much smaller, and so far we haven't reached the stage that we have components which are better interpretable. So for this, in this application, just using deep learning gives us better results, I would say, or I don't see the benefit so far to use the factorization. So it depends on, I think, on the application. So if you have, I would say, if you have bigger areas, such as in brain tumor, you can have a benefit of using these NMF or tensor factorizations as extra layers.
Thank you. I think, yeah, A couple of, maybe one more question. We're going to get quick, I think, going, I guess. So 15. Yeah, we want one more question. Yeah, you have it. Go ahead. You have
Okay, me?
Yeah, go ahead. Yeah.
So in the spectroscopy results that you showed, and you said the water has the highest, very, very high spectra, right? And then you said that there are two methods to remove this one, so you can see the lower one. Wouldn't it be easy to remove it because it's the highest, so you remove the highest signal? Can you elaborate, like, you said two methods to you, I feel like you can use a filter and.
In fact, you have to look at the water component has very long tails. So if you just use a filter, you will cut the tails, and this will generate a bias to the metabolites you want to quantify. So you really have to model it so that you can, at the same time, in the water region, also remove the tails of so it's the natural pattern of a metabolite is really like an exponent, so-called Lorentzian, in fact, with big tails that also need to be removed. So you need to model it, and you can clearly see that this really enhances the quantification of the remaining metabolites.
Okay. Sorry, we cannot take more questions. We're getting late here. This was a wonderful talk. A lot of questions, a lot of discussion. Let's thank the speaker again. Thank you very much.